topic is analog RF parameter analysis of gallium nitride nanowire. In this video, I will cover the following topic. First one, why we use gallium nitride. Second, gallium nitride nanowire growth methods. Third one, growth mechanism of gallium nitride nanowires. Fourth one, applications of gallium nitride nanowires. Fifth one, gallium nitride used in field effect transistor. Sixth, analog performance parameters analysis. And the last but not the least, RF parameter analysis. Let's start with the gallium nitride nanowire. Gallium nitride nanowire has attracted much attention due to its wide bandgap, high melting temperature, carrier mobility, strong chemical stability, and high electrical breakdown field have demonstrated great potential in device applications, including field effect transistor, light emitting diodes, ultraviolet photodetector, and laser applications. Gallium nitride is an important 3,5 semiconductor material with a direct band gap of 3.4 electron volt at 300 Kelvin. The wide direct band gap makes gallium nitride an attractive material for various applications. Gallium nitride nanowires have demonstrated significant potential as fundamental building block of nanoelectronics and nanophotonics devices, and also offer substantial promise for integrated nanosystem. The successful synthesis of gallium nitride nanowire has been demonstrated by various methods including chemical vapor deposition, laser ablation, metal organic chemical vapor deposition, molecular beam epitaxy, and hybrid vapor phase epitaxy. In the next slide, we will discuss the various gallium nitride nanowire growth methods. I am not going in the detail of these methods. I am giving only the brief idea about these methods. First one is the chemical vapor deposition method, CVD. CVD is a chemical process often used to produce high purity, high performance solid materials. CVD method in a conventional tube furnace is widely used by researchers to synthesize nanowire due to its advantages of facile, simple and cheap. In the past decade, gallium nitride nanowires have been prepared by CVD by many other groups. A simple method for large-scale production of gallium nitride nanowires on silicon wafer by reacting gallium and ammonia GaNs using polycrystalline indium powder as a catalyst. In the preparation of the nanoelectronics devices, it is very important using nanowire with low defect density and long length. So that we have preferred this CVD method. Another is laser ablation and another is metal organic chemical vapor deposition. Laser ablation is a laser assisted method, and the key feature of this technique is that the catalyst used to define nanowire vapor liquid solid growth can be selected from phase diagram data and on knowledge of chemical reactivity. Another method is metal organic chemical vapor deposition. In this method, it is a chemical vapor deposition method of epitaxial growth of material from surface reaction of organic compounds or metal organic and hybrids containing the required chemical elements. Another method is molecular beam epitaxy. Molecular beam epitaxy is a method to deposit single crystals. In this technique, nucleus process of gallium nitride nanowires in terms of nucleus density and wire evolution with time for a given set of growth parameters were investigated. Another method is hybrid vapor phase epitaxy. Hybrid vapor phase epitaxy is an epitaxial growth technique often employed to synthesize semiconductors such as gallium nitride, gallium arsenide, indium phosphide, and their related compounds. Hybrid vapor phase epitaxy provides a better process control than the commonly used CVD techniques and is of particular interest due to its high growth rates and simplicity of basic reactor design. Next is the growth mechanism of gallium nitride nanowires. The growth of nanowires is a process involving the use of anisotropy. To obtain anisotropy, many methods have been adopted, which can be roughly divided into two kinds: vapor method and solution method. Vapor method mechanism includes vapor liquid solid VLC method, vapor solid VS method, vapor solid solid VSS method. Next is the solution based mechanism includes solution liquid solid SL method, solution solid SS method. If you want to study in details growth mechanism of gallium nitride nanowires, you have to follow review paper based upon nanowire gallium nitride device. I am not discussing about these methods in details in this presentation. Characterization of gallium nitride nanowires. Various tools have been used to realize the characterization of gallium nitride nanowires. The most common used instruments in the reported literatures are scanning electron microscope, X-ray diffraction, transmission electron microscope, Raman spectroscopy, and photoluminescence spectra. Applications of gallium nitride nanowires. As an important direct wideband gap material, semiconductor material, gallium nitride has been widely used in ultraviolet or blue emitters and high temperature, high power electron devices. Gallium nitride is also a promising material for field emitters because of its low electron affinity and high carrier mobility, as well as its excellent physical and chemical stabilities. Next, for semiconductor nanowires, the cylindrical geometry and strong two-dimensional confinement of electron, hole, and photons make them particularly attractive as potential building block for nanoscale electrons and optoelectronic devices. The application of gallium nitride nanowires have been demonstrated by the researcher in these fields: photovoltaic device, light emitting diode, field effect transistor, laser, photocatalyst, and nanogenerators. In this presentation, I will discuss only one application of gallium nitride, that is field effect transistor based structure. Let's start the analog RF performance analysis. In this video, analog RF figure of merit of silicon nanowires are studied and simulated, including transconductance efficiency, GM by ID. GM is the transconductance and ID is the drain current. Intrinsic gain, GM divided by GDS. GDS is the output conductance. Cutoff frequency Ft and the maximum oscillation frequency Fmax. In the literature, it is observed that the silicon nanowires and the silicon nanowire tubes exhibit superior intrinsic RF scaling capability and are suitable for low application analog RF applications. The main figure of merits of analog RF technology are transconductance efficiency GM divided by ID, intrinsic gain GM divided by GDS. This is not GD, this is GDS. GM divided by GDS, cutoff frequency Ft, and the maximum oscillation frequency Fmax. First, we will discuss about the analog performance. Transconductance efficiency, CGS and CGD in SILVACO ATLAS device simulator. For finding the CGS and CGD in your ATLAS simulation deck after voltage sweep, add AC frequency is equal to 1 MHz. If you want to obtain these results, that is based upon conductance and the capacitance, you have to add AC frequency in your code. Then small signal AC simulation will be performed for each gate wise for 1 MHz frequency. Transconductance efficiency. Transconductance efficiency TGF is equal to transconductance divided by drain current, where transconductance, you know very well, it is equal to change in drain current with respect to change in gate voltage. It is clear from the equation that with high dielectric material, exhibit higher TGF as compared to lower dielectric structures. As the dielectric permittivity increases, the GM by ID ratio decreases and it becomes worst at K is equal to 30. Higher TGF is not good for high linearity microwave system, as lower TGF is not drawback since the power consumption in sub-threshold region is very less. The output conductance GDS is calculated as change in ID with respect to change in VDS voltage, drain to source voltage. The drain current is increasing with increase in high K dielectric permittivity, which in turn makes the GDS high for these configuration. CMOS analog circuits require transistor with low output conductance in order to achieve high gain. High GDS means low output resistance, which resulting an increase in ID with VDS in saturation region. The device has a good control over channel length modulation and DIBL owing to its low GD value. The on resistance is inversely proportional to GDS. R on is equal to 1 divided by GDS, output conductance. The next analog performance parameters are early voltage and intrinsic gain. The variation of the early voltage VAA and the intrinsic gain AV as a function of gate overdrive voltage. What is the gate overdrive voltage? Gate overdrive voltage is equal to gate source voltage minus threshold voltage. It is called as overdrive voltage. For better analog performance, the early voltage and intrinsic gain should be as high as possible. The formula for the early voltage is defined as the ratio of drain current divided by the GDS, output conductance, and the intrinsic gain is equal to GM, transconductance, and divided by GDS, output conductance. By using this formula, the intrinsic gain is equal to transconductance efficiency into my early voltage. The intrinsic gain is a variable figure of merit for operational transconductance amplifier. It is observed that with increase in dielectric permittivity, the gain of the device becoming worst. Next, we will discuss the RF performance parameter analysis. The important high frequency or RF circuit parameter includes cutoff frequency FT, transconductance frequency product TFP, gain frequency product GFP, gain transconductance frequency product GTFP. First, we will discuss the first RF parameter, cutoff frequency. Cutoff frequency is defined as the frequency where the current gain is equal to unity. Cutoff frequency by mathematical formula is defined as equal to Gm transconductance divided by 2 pi CGG. We know that CGG is the total gate capacitance and the value of the CGG is equal to CGD plus CGS, where Gm we know that it is a transconductance delta ID upon delta VGS, and the value of pi is 3.14 and CGG is the total gate capacitance. You can obtain capacitance of the gate using AC solution. This means after applying AC frequency, you can find out these parameters CGD and CGS. After adding, you will get the total gate capacitance. By an AC solution, you can have drain current versus gate voltage 2 value. Then you can define proper function satisfying above equation of FT in Tony plot and enjoy. The code for cutoff frequency you can use dx drain current gate voltage, and 3.14 multiplied by 2 is equal to 6.28 into my absolute total gate capacitance value. Next is the RF parameter, transconductance frequency product, gain frequency product, gain transconductance frequency product. First, gain frequency product is equal to Gm divided by GDS into my cutoff frequency. Transconductance frequency product is equal to Gm divided by IDE, drain current, into my cutoff frequency. Next, gain transconductance frequency product is equal to Gm divided by GDS into my Gm divided by ID into my FT. It is equal to intrinsic gain into my transconductance frequency product. TFP, transconductance frequency product, represents a trade-off between power and bandwidth, and it is utilized in moderate to high speed design. Similarly, gain frequency product GFP is also very important parameter for operational amplifier in high frequency applications. Both the GFP and TFP are started linearly increasing as BGT increases in subthreshold region and hold an optimum value, then start decreasing in the saturation region. This means if you are increasing the gate overdrive voltage, first GFP and TFP start increasing in the saturation region, and after that it can hold an optimum value and then start decreasing in the saturation region. And last but not the least, maximum oscillation frequency, F maximum. The maximum oscillation frequency is defined as the frequency where the power gain is equal to unity, and the formula for the F maximum is equal to cutoff frequency divided by 2 into square root of GDS into RG plus RS plus 2 pi cutoff frequency Rg into CGD, and its approximate value is equal to under the root of cutoff frequency divided by 8 pi into my Rg CGD, where Gm is the transconductance, CGS and CGD are the gate source and the gate drain capacitance respectively. GDS is the output conductance. Rg and Rs are the gate and the source resistance, and the value of the Rg is equal to 1 divided by gate transconductance. The value of the gate transconductance you can find out by simply export the value of the log file. I will show after run the program the value of GGG. Next is the cutoff frequency FT. You know that Gm divided by 2 pi into my CGG. Next MT is equal to 1 by square root of 4 into Rg into GDS plus 2 pi FT CGD, and the value of the F maxima is equal to cutoff frequency into MT. You can use both formula. Both formula actually are same. You can use this formula F maximum, and you can use and this formula F maximum is equal to cutoff frequency into MT. Both are same. Let's go to the code. Again, start from the Go Atlas. This time I am using variable parameter code. The advantage of this variable parameter code is no need of change of meshing, doping and electrode positional parameter while changing the geometric parameter such as length, width of the device, or you can change the thickness of the oxide. If you are changing the gate length and thickness of the oxide, the code will automatically adjust meshing, doping and other statements in Atlas input file. In this code, I am not using cylindrical parameter. I am designing two-dimensional nanowire gallium nitride structure. The benefit of plotting 2D structure, it will eliminate the convergence problem of 3D structure, and also it reduces the runtime of the code. By using the set command, I have set the length of the source region is 10 nanometer. Length of the drain region is again 10 nanometer. Length of the channel, or we can say that the gate length, is 20 nanometer. Thickness of the oxide 1.5 nanometer. Thickness of the oxide 2 is 1 nanometer. Spacer length is again 10 nanometer. Radius 5 nanometer, and the TM is 1 nanometer. I have defined some more set term. The structure is start with the 0. First region I have defined with the start from the TM, and the second region start from the LS. I have defined the different region using the variable parameter. Next, I have defined some variable parameter in the radius term also. Next, I have defined the variable parameter in terms of radius also. I have defined some fixed value for the radius meshing. Next, I have defined first the X meshing using variable commands. In the X meshing, start from the start R with the spacing using the variable parameter. If we are changing the length, thickness of the device, these meshing are changing automatically. That's why we are using the variable parameter for the X meshing. I'm not using the angular meshing because we are defining the structure in 2D mode, so that we don't require angular meshing. Next, I have defined the Y meshing using variable parameter. Please note down the code very carefully. If you are making a single mistake, then this code will not run on your computer. Please note down every parameter, every meshing, every variable very carefully. After defining the Y meshing, I have defined the reason statement with their material. Reason number 1, having material air with their positional parameter. Reason number 2, having material gallium nitride with their positional parameter using variable command. Reason number 3 is silicon dioxide material with positional parameter using variable commands. Reason number 4 is again oxide but different material, aluminum dioxide, with their positional parameter. And reason number 5 is SiO2. Reason number 6 is HFO2, and the reason number 7 is HFO2. Every reason defined with their positional parameter using variable code. Next, I have defined the electrode statement. Electrode name gate, source 1, source, drain 1 with their positional parameter using variable code. Next, I have defined the doping. In this structure, I am using the charged plasma concept. In the charged plasma concept, you have to taken uniform doping or intrinsic doping overall the substrate, that is equal to 10 raised to power 15. So I have taken the intrinsic doping 10 raised to power 15 with their positional parameter using variable code. If you are designing the charged plasma structure, that you must have to define work function at the source and the drain end. At the source end, I am using 3.9, and at the drain end, I am using the same 3.9 electron volt. If you don't know about the charged plasma concept, you must follow my previous video based upon a biosensor, in which I have mentioned in detail about the charged plasma concept. But in the previous video, I am using FET, so that we have applied different work function at the source and the drain end. But in this I am using FET structure, so that we have applied the same work function at the source and the drain end. The gate work function is 4.72 electron volt. Source and drain work function is 3.9 electron volt. After that, the model statement I have already mentioned in my previous video. Method statement, this code, output valence band electric field for obtaining different parameter from the structure. Next, I have defined the voltage at different terminal, starting from the VG0 and the V drain 1 volt, and the gate voltage start from the 0 to 1 volt. If you find out the conductance and the capacitance, you must define AC frequency at the beginning of this solve statement. After that, here I am using the plot command to extract the data. Next, for extract the different parameter, you have to define the file name. You can find out the transconductance GM, delta ID upon delta VGS. Next, mobility. Next, I off, I on, and the different parameter you can find out. If you run this program, you will get two files. One is the structure file and one is the log file. This is the log file. drain current with respect to gate voltage. I want to check in the log format. Now y-axis is in log and the x-axis is in linear scale. The on current is approximate 10 raised to power minus 4 and the off current is approximate 10 raised to power minus 13. This is the structure file in 2D format. This is the air. This substrate material is gallium nitride. At the source and the drain end I am using the silicon dioxide. Spacer I am using the aluminum dioxide. And gate oxide is hafnium oxide, HFO2. If you want to find out analog RF performance parameter, you need three graphs. One is the ID drain current. I have shown you will find the drain current. Second parameter is the GM transconductance. By simply using this command extract name GM curve v dot gate dy dx v gate I drain out of GM transconductance, you will find out the transconductance value in that format. By using Tony plot, you can open this DAT file. My dear friend, this is the DAT file. GM underscore charge plasma DAT file. This is the transconductance value. I have obtained ID and the GM. If you want to obtain GDS, then you have to do one thing. You have to change something in the code. You have to replace VGS with VDS and VDS with VGS. So please note down very carefully to find out the value of GDS, output conductance. Solve initial. After that I had given gate voltage 0 and gate voltage 1 volt in place of drain voltage. In the previous code I have defined first drain voltage, then after that gate voltage. In this code first I have defined the gate voltage 0 and direct 1 volt. After that solve name drain P drain 0 to 1 volt with the step size 0.01. And in the extract command you have to simply replace gate with the drain. In the previous code I am finding the delta ID upon delta VGS to find out GM. To find out GDS you have to replace gate with drain. Simply you have to find out delta ID upon delta VDS. So we have taken drain at the gate point, V drain dy by dx, V drain, I drain current, I drain is same. Only the gate voltage is changing from to the drain voltage. And the GM charge plasma GDS DAT file. If you run this code, you will find out the output conductance DAT file. My dear friend, this is the GM transconductance and this is the output conductance GDS. So we have found three different curves. First, drain current versus gate voltage. Second, transconductance GM versus gate wise. And next one, output conductance with respect to drain voltage. By using these three curves, you can find out every AF and RF parameter. Let's go to the PPT. Transconductance efficiency, GM by ID. I have already find out GM and the ID current. By dividing these values one by one, you will find out the transconductance efficiency curve. To obtain the value of this R on resistance, you have to simply divide the output conductance. 1 divided by output conductance, you will find out the R on curve. Next is the early voltage, VEA. By simply dividing the value of ID, drain current, and output conductance, you will find out the early voltage curve. Next is the intrinsic gain. Intrinsic gain is depend upon the GM and GDS. We have already find out transconductance and output conductance by dividing these value one by one, or you can multiply the transconductance efficiency to the early voltage to find out the value of intrinsic gain AB. Next is the cutoff frequency. To find out the value of cutoff frequency, we have find out GM. We know the value of pi 3.14, and the value of the gate capacitance you will find out by simply adding AC frequency is equal to 1 megahertz into the code. You will find out the value of CGD and CGS. By adding these two values, you will get the total gate capacitance. For finding the value of GFP is equal to GM by GDS, we know that GM and GDS multiply with the cutoff frequency. GM by GDS is equal to intrinsic gain. By simply multiplying the value of intrinsic gain and the cutoff frequency, you will find out the gain frequency product curve. For find out the transconductance frequency product curve, we know the value of GM and ID. By dividing the value GM and ID one by one and multiply with the cutoff frequency, you will find TFP, transconductance frequency product. And the last one, gain transconductance frequency product. By simply multiplying the value of intrinsic gain and TFP, you will find the value and the curve of gain transconductance frequency product. And last one, maximum oscillation frequency. For finding the value of the maximum oscillation frequency, you must know FT. We have already find out the value of cutoff frequency and the value of MT. The value of MT contain RG parameter. The value of the RG is the gate resistance. You will find with the value of GGG. I will show GGG value. When you export the log file, you will find these value: frequency, drain voltage, drain current, in which one of the parameter is CGG. This is not the CGG, this is the GGG, any transconductance at the gate terminal. For finding the value of RG, you have to divide 1 divided by these GGG, transconductance at the gate terminal. You already know the value of GDS, output conductance, pi, FT and CGD. By simply putting the value of these parameters, you will find out the maximum frequency. My dear friends, by simply find out the three values: drain current, GM transconductance and GDS, output conductance, you will find out all the parameters, analog and radio frequency parameters. My dear friend, this is the end for today. Please stay tuned for more interesting videos.